Greetings, everyone. My name is Yogesh Pandian, and today I'll be introducing and covering the key parts of our final presentation on mechanics of fracture and failure in solid-state electrolytes for lithium batteries. This is team number 13, and I'm Yogesh Pandian, and I have my teammates Deshwar and Jahin and Prashant Sundaravardhan. So these are the table of contents that me and my teammates will be running through today. So coming to the introduction part, why solid state batteries? So solid state batteries offer several advantages over traditional lithium ion batteries. Basically, they are safer as electrolytes are non-flammable, and they can also support lithium metal anodes, and they offer much higher energy density. However, the major roadblock to commercialization SSBs over lithium ion is mechanical failure, especially inside the brittle solid electrolytes that are central to these batteries. So while they hold promise, the key issue remains durability under cycling conditions. So some of the topics and the research papers covered here is the types of mechanical failures in solid electrolytes and failure mechanisms at multiple scales, modeling approaches and simulation results. And also we're running through the experimental validations from several research papers using real-time methods. And finally, the key mitigation strategies and future research directions. So moving on to my teammate, Jahin.
Hi, everyone. I'll be covering the types of fractures and failures. Next slide, please. So first we have the surface cracking. It's mainly silicon-based electrodes. The tensile stress builds up at the film surface during the lithiation process. As lithium diffuses into silicon, the transition from compressive to tensile stresses occurs. This stress exceeds the fracture strength to the silicon material, causing the cracks on the surface. And these surface cracks lead to the mechanical failure of the electrode, reducing the capacity. Next, we have pulverization. The cause is silicon experiences large volume changes up to 300% during the lithiation and delithiation cycles. And these extreme volume changes cause the silicon structure to fragment repeatedly. That fragmentation results into a loss of electrical contact between the silicon particles and severely degrading the battery performance over the time. Next slide. The elimination. The mismatch in strain and stress between the lithiation layers and lithiation process underlying the substresses that accumulated the tensile stress over the cycle leads to debonding at the interface, especially under the plane strain conditions. And this leads to peeling or separation of the silicon film from the substrate and compromising the integrity of the electrodes. Next, we have parallel or network cracking. The cause of this, the residual tensile stress isn't present in the thin silicon film, and the crack form in a relief mechanism propagating in a regular pattern. These cracks form a parallel or a network-like pattern which has the characteristic of spacing around 10 nanometer and weakening the electrodes. Next, we have the stress mismatch induced the fractures. The causes differences in the mechanical properties in lithium and dilithium process in silicon cycle in silicon and the differences in elastic modulus in yield stresses. This difference creates a non-uniform stress distribution which leads to localized fractures in the material. The structural failure can occur even before the full lithiation process is achieved and causing the significant degradation in battery performances. Next slide, please. Next, we have the solid electrolyte interface, also called SEI fracture. The cause is during the lithium intercalation and deintercalation process, the volume of graphite changes. As the graphite expands and contracts, the SEI, which coats the active material, undergoes a mechanical stress. The SEI experiences the cracking due to the constant expansion and contraction of the graphite. When the SEI cracks, the electrolyte can penetrate into the active material, leading to the formation of more SEI and consumption of lithium ions. This results in gradual capacity fade in the battery over time. and also fatigue-induced fracture due to the cyclic mechanical loading. Next, we have the active material fracture. The cause is diffusion-induced stress, DIS, arises from lithium concentration gradients within the graphite during the fast charge and discharge cycles. High charge or discharge rates and large particle sizes or low temperatures generate large stresses, which can induce mechanical fracture in the graphite. Structural damage occurs in the graphite, leading to a loss of electrical conductivity, which degrades the performance of the battery. Main particle fracture under extreme conditions, such as low temperatures like 10 degrees Celsius. Next slide. Debonding. A mismatch in the radial and the tangential stress at the interface between the ACI and the graphite level. The mechanism follows cycling swelling and shrinking of the graphite during the cycling, leading to the failure at the interface level. This failure reduces the mechanical integrity of the electrode, increases the internal resistance, which hampers the battery's overall efficiency. Fatigue failures. Also, cycling stress cracking. Repeated mechanical cycling under the sub-yield stress level can eventually cause failure. According to the SN curves and Basquian law, even the low amplitude cycling stresses can result in failure after many cycles. Accumulation of micro cracks over time leads to an eventual crack in the ACI and the graphite level, causing the performance degradation. Last, we have the capacity fade, which is functional failure resulting from fractures. While not a direct fracture event, but capacity fade is a consequence of mechanical degradation that's caused by the continuous formation and repair of the ACI. As the ACI cracks and reforms, lithium ions are consumed in a process which leads to a loss of available lithium for charge cycles. This results in the reduced capacity efficiency of the battery and material cracking cause electrical isolation. So understanding these failures mechanism is very crucial for improving the design and the longevity of the lithium-ion batteries. By addressing the causes of mechanical stress and material degradation, we can develop more durable and efficient battery technologies. Innovations such as advanced electrode materials, improved ACI stability, and better manufacturing techniques will help mitigate this situation and issues to ensure more reliability for lithium-ion batteries for a range of applications. Next slide. This is a summary table for all the types of fractures and failures, the material which are affected, the cause and the condition, and the result, which is a result of the types of fractures and failures in lithium-ion batteries. Next.
Hi, this is Sudeshwar Yamgekar. I'll be going through failure mechanism at different scales. So let's begin by looking at next slide. So let's begin by looking at failure mechanism at macro scale, specifically how electrode volume changes during charging and discharging affect the solid electrolyte. In this study by Budiman, they molded solid state batteries using LGPS as the electrolyte. What's key here is the mismatch in expansion between the anode and cathode material. For instance, indium expands by over 105%, while the NCM cathode actually shrinks by 7%. This mismatch builds up a significant comprehensive stress within the solid electrolyte, especially during the fast charging. Uh, Simulations using ABQs showed that the von Mises stress reached values above 2.8 GPa, far exceeding the yield strength of electrolyte. At the interface between the indium anode and LGPS, they observed shear failure initiating at about 800 MPa. Among the stimulated setups, the NCM LGPS in configuration showed the most severe damage due to opposing volume changes from both sides. The highlights this highlights that mechanical failure starts early, right at macrostructural level. Next slide. Uh, Moving deeper into the material structure, Budiman's team also studied how the grain structure of solid electrolyte affects mechanical integrity. They compared monocrystalline, uniform polycrystalline, and random polycrystalline models. In all cases, the electrolyte experienced high stress concentration, but the polycrystalline type showed significantly more failure. That's because cracks tends to initiate at grain boundaries, which are structurally weaker. The von Mises stresses distribution exceeds 2 GPa in many zones, especially around the electrolyte interface. As a result, plastic deformation was observed at both the center and edges of the electrolyte, compromising ionic conductivity and long-term battery reliability. These findings suggest that while polycrystalline materials are more common in real-world application, they inherently poses a greater risk for crack propagation. Next slide. Now let's zoom in to the micro scale level and explore what happens at individual grain boundaries. According to Giao, one of the key factors determining key behavior is strength ratio between the grain boundary and grain itself, denoted by the parameter lambda. When lambda is less than zero point 0.2, crack follows the grain boundaries. This is known as intergranular failure. As lambda increases to between zero point 0.2 and zero point 0.9, failure begins to transient. Cracks start to propagate into grain themselves. At lambda equal to or above zero point 0.9, we see full transgranular failure, where cracks cut directly through the grains. Importantly, all these cracks originate from the tips of growing lithium filament. This insight is critical because it means that failure can be tuned or at least delayed by strengthening the grain boundaries relative to the grains. Next slide. Taking it a step further, the same study also evaluated the role of grain boundaries with detonated delta in nanoscale damage evaluation. They found that where grain boundaries width exceeded about 21 to 31 nanometer, depending on the value of lambda, transgranular cracks become dominant. Wider grain boundaries lead to more stress dissipation and ultimately larger displacement within the structure, which in turn make the electrolyte more prone to catastrophic cracking. In practical terms, this means solid electrolytes should be engineered with both narrow and mechanically strong grain boundaries to resist failure under lithium filament growth. Next slide. To summarize, the failure mechanism of solid state batteries are scale dependent and multifaceted. At macro scale, volume mismatches between electrodes can regenerate extreme stress. At micro scale, weak grain boundaries promote intergranular failure, and at the nano scale, both boundary strength and width govern how crack propagates. So, how do we design more robust batteries? One approach is carefully select electrode materials with matching explosion properties like LTO, which showed minimal expansion. Another strategy is to engineer grain boundaries either through material processing or additives to reach a strength ratio lambda above zero point 0.9 and keep delta below 20 nanometer. So moving forward, Yogesh will take over.
So, in the core of my section, we'll look at the 4 key strategies used to prevent mechanical failure in solid state electrolytes. So, these are These are material optimization and stress relieving design and interface engineering, and also multiphysics modeling. These are based on the simulation driven work from paper 5 and paper 6. These are real time experimental insights. Moving on to the next part. So, paper 5 introduces a coupled electrochemomechanical model to simulate how stress builds during battery cycling. It maps out when fractures form and how the internal structure evolves under stress, particularly near interfaces between electrodes and solid electrolytes. And also in this slide, you can see the 2D model in plane strain of the composite negative electrode from paper 5. Moving on to the next slide, where we're going to discuss about the design factors that influences the stress. Um, so these two graphs are gives the takeaways on the left. A low Young's modulus ratio, which leads to faster crack growth, and also on the right side, higher active material content and lower interfacial strength leads to early failure. These two graphs basically tells us that the matching in material stiffness are improving the interface strength, which are critical to long-term battery performance. And moving on to the next slide, paper 6 basically shifts to the real-world experimental work. So using operando techniques, the researchers observed how ion migration and internal defects lead to mechanical failure. So they show that the defects like Schottky and Frankie centers serve as ion traps, which concentrates stress and making the system vulnerable to dendrites and cracks. And moving on to the next slide, continuing with a real world experimental observation in paper 6, these interfacial degradation are visualized. The schematic shows 4 stages of interfacial degradation. It starts with stable lithium transfer, then simulates ion plus electron movement into the electrolytes, and followed by lithium plating, which in turn forms void, basically called as void formation, and finally collapse of the interface. These findings are crucial for interface design. They prove that mechanical plus electrochemical failure are deeply connected together. So moving on to the next slide, this strategy table based on real observations from both paper 5 and 6. So the summary table gives the observation that using coatings to block lithium penetration and introduce soft interlayers to absorb interface stress and to adjust cycling protocols to reduce void formation. These are real applicable strategies that come straight out of both modeling and experimental studies. So final notes on design integrations are the takeaway here is that building mechanically resilient SSBs is not a single solution problem. It requires simulation-based prediction, real-time diagnostics, and also smart material interface design. Bringing these together will allow to push solid-state batteries toward commercial readiness and replacing lithium-ion batteries slowly from the market. Now, my teammate Prashant Sundaravardhan will continue the final mitigation strategies.
Hello everyone, myself Prashant Sundaravardhan will cover about the topic final mitigation strategies and advanced research. Next slide. Okay. As we bring our discussion into a more practical light, let's consider what all this means for battery design. Mechanical integrity isn't just about choosing the right material. Grain orientation and grain boundary strength is also just critical. If those are weak, crack starts earlier even with the ideal materials. That's why we need next-gen batteries must integrate with the mechanical buffering layers, materials that can flex or deform without fracturing. Another key point is that bonding across interfaces. If there are voids or weak bonds at the grain boundaries of electrode interfaces, stress concentrate there and triggering their early failure. The idea now is not just to strengthen the individual material, but also to the co-engineer everything, the grains, the coatings, the interfaces to work in the sync. Next slide. Internal versus interfacial breakdown. So one more thing to understand is that failure doesn't happen in isolation. You have internal breakdown where lithium builds up and causes microcracks. But you also have interfacial breakdown like voids and delamination at the electrolyte boundary. These two effects feed into each other, so which causes the crack from inside, which worsens the edge and vice versa too. The takeaway here is fixing just the core or just the interface isn't enough. We need to design solid electrolytes and the interfaces together such that stress is balanced and failure is minimized across the entire structure. Next slide. So microstructural innovation needed. At this point, it's clear that chemistry alone won't solve the solid state battery failure. We also need smart microstructural engineering. Let's start with grain boundaries. In polycrystalline materials, crack often begin and propagate along these boundaries. So optimizing grain boundary chemistry, making them stronger, more adhesive, and more crack resistant is crucial. Even just aligning grains in a specific orientation can grammatically reduce the stress concentrations. Another key idea is to design coatings that are ionically conductive, so lithium ions can move freely but electronically insulating. This prevents internal short circuits and uncontrolled lithium plating. If if electrons sneak through, it can lead to side reactions of filament growth, both of which cause mechanical and electrochemical failure. On top of that, using nanostructured materials often advantages. Smaller grains or layered composites can redistribute stress more uniformly, reducing localized failure zones. So to summarize, our goal isn't just to stop cracks, but to design microstructures that don't allow cracks to form in the first place. That's a major shift in how we think about battery reliability. Next slide. Dead lithium and mechanical instability. A big consequence of mechanical damage is dead lithium. This is lithiums that's still inside the battery but can't participate in charging or discharging anymore. Cracks in the solid electrolyte or separation of the interfaces isolate parts of the lithium. Over time, this lithium accumulates, becomes inactive, reducing how much energy the battery can store. This slide visualizes how lithium filaments bypass the a correct path due to the cracks. These due to eventually isolate the lithium and break the ionic pathways and hurt the battery's long-term performance. And the type 2 is that it happens inside the solid electrolyte when crack form, they close and trapping lithium inside. Both these types leads to permanent capacity loss and tend to build up over time. Real-time NMR studies shows that these two processes evolve simultaneously. That's why interface engineering matters so much. We need to maintain both ionic and electronic pathways to keep lithium connected and active throughout the battery's life. Now, next will be continued by Yogesh.
Thanks, Prashant. So the conclusion and future directions will be taken over by me. So to conclude, while solid-state batteries hold exceptional promise, their mechanical instability is still a serious limitation to commercialization. We've seen how fractures begin from stress accumulation, mismatch, and degradation of interfaces. But with simulation and in-situation monitoring, we can now predict and respond to failures more intelligently. This will help us to, in the future, to commercialize SSBs, solid-state batteries, more than lithium-ion. And moving on to the future directions, looking forward, research needs to focus on ductile solid electrolytes that resist cracking, and machine learning plus multiphysics simulations to identify failure points is mandatory here. And more to use of operando spectroscopy and imaging to conduct real-time experimental studies over materials and material selection. And finally, a cost-effective scaling methods for commercial application. It's going to take a team effort from materials scientists to engineers and to a bunch of other people to make solid-state batteries truly viable. But in order to replace flammable and insecure lithium ion from the market to commercialize solid-state batteries, the future directions will lead to that. So thank you. That wraps us our presentation. Thank you for listening. We are happy to take any questions you have through emails. Thank you.